Here is how to count the number of surjective functions between two finite sets. We denote the first finite set with 0 all the way up to n minus 1, enumerated by n, and the second set with the natural number m. We want to count how many functions there are from first one to the second one that are surjective or onto. And we're going to use the inclusion-exclusion principle, which, as you can see here at the top of the screen, tells you how to compute the size of a union of finite sets. And it is basically by iterating and adding the different intersections within subsets of this family. The first question is, if we define the following family of sets for every j less than m, again, m is the codomain of these functions, Sj will be the set of all functions that don't contain j in their image, those that miss j. If you can see the sketch in green, it's all functions that do whatever you want outside of j, but j is not in the image. There's no arrow pointing to j. So if you take a finite subset of the codomain, non-empty finite subset of the codomain so that this makes sense, then what is the size of the intersection? First of all, what is the intersection of all the sj's? Well, if sj is the set of functions that don't contain j in the image, then the intersection over this family, I'm looking at this set down here, would be the set of functions that don't contain any of the elements of capital J in their image. So it's the functions that miss all of those things. And it shouldn't be too hard to convince yourself that the following is true. Given for any function that is inside this intersection, the codomain of f is some subset of size m minus the size of j. It is actually exactly this set, right? You take the codomain and you remove everything that is in j, because those are the elements that don't get hit by anything. Maybe there are more elements that don't get hit, but the point is that at least the elements in j for sure don't get hit. And conversely, any such function f that satisfies that the domain doesn't contain j or is actually disjoint from j has to be inside this intersection because none of the elements of capital J get hit. What this tells you is that this intersection is actually exactly the set of all functions from n, from the set n, to the set m minus j. So we know the size of that. And interestingly, the size only depends on the size of j. So the conclusion from this brief discussion is that this has size m minus whatever size j has, which we don't really know right now, to the nth power. And the interesting thing is that this number that I'm encircling in red does not depend on the set j, only the size of the set j. Meaning if you swap out elements of j, the same size is valid for this intersection. This will be useful in a little bit. The second question is, what is the size of the union of all of these sj's? And for that, we're going to need the theorem. So the union basically is equal to this sum. And I'm just going to copy that sum as it is written in the inclusion-exclusion principle. So we know that this is equal to the sum over all of the j's inside M. Again, we're using this notation for natural numbers as sets, right? Maybe I should write this at the top as a reminder. This is the same as n, just to simplify the notation and not have to rewrite the stuff. Okay, so this is the sum over iterating terms where this is the size of j plus 1. And here we have to include the size of these intersections. But these intersections, we just computed the size, so we might as well substitute this back in. So this is the set of j m minus 1, j plus 1. And we just computed this as m minus the size of j to the nth power. And it seemed like now we are stuck. This doesn't look anything like what we want yet. Notice that this sum has way too many terms. If we want to write this as a closed form using an enumeration that only depends on m, well, this is way bigger, right? There's a lot more subsets of m than there are elements in m. So this doesn't quite look like we want yet, but there's a way to simplify it. And the trick is to notice that none of the terms in these sums depend on j, only the size of j. Here's a trick. For every natural number k, let's say of size m, at most size m, and every j subset, okay, we have to exclude 0 for this to make sense. So every 0 k m and every j of size k, notice that the following is true. We already agreed that this has just size m minus the size, which in this case is k, right? There are how many such subsets j can we find? J is a subset of m of size k, so it's m choose k, right? Maybe let's say such sets j. Now this is helpful because if we continue up here, and you'll have to find a better way of writing this, of course. So continuing from up here, what we can do is we can separate that sum into different chunks depending on the size of j. This sum is adding over all the possible subsets j. So maybe I can be a little bit more organized and say, let's add all the ones that have size 1 first, all the singletons first, right? So why don't we go ahead and do that? What I want to do is I'm going to write the sum am, and I'm going to first add all the j's that have size 1, then the ones that have size 2, size 3, and so on for every k. This is clearly the same as before. I'm just separating them, rewriting this using associativity, right? I'm adding them in a specific order, and the notation that I have written above doesn't really imply a particular order. Not that it matters, because of course it's all commutative and associative. Okay, now this seems like we just made things more complicated, but notice that if I just copy this row right here and paste it down here, there's something that we can do. Notice that every term inside this sum has the same size of j, right? So we can just substitute this in. So instead of writing the size of j, let's just write k, right? And notice that this is important because then this sum, the summands don't depend on j anymore, just on k. And k is indeed the variable that I want to end up writing this in. So what I'm saying is this sum, the one that I will now encircle in green, this sum is adding the same number many times. The same number is this number right here, right? This doesn't change depending on j because it only depends on k, which is fixed for every summand. So how many terms do I have? Well, it's how many j's. How many such j's can I find? So this doesn't change, but this is not a sum, it's actually just a product. So I'm multiplying m choose k, which is all the possible combinations of j, of such j's that I can find. And for each of those, I'm adding one of these numbers. All I have to do is multiply them, and I get this right here. And if you reorganize this a little bit, you'll notice that this is actually already in the form of the final answer. One more question is, what is the union that we just computed the size of? Well, something is in the union of Sj if for some j the function doesn't hit that j. So this is the set. It is of non-surjective functions from n into m, right? And that tells you what the final answer should be. So how do we conclude from here? We know that in total there are m to the n functions. So if we only want the surjective ones, well, we have to remove the ones that aren't surjective. So we remove everything that's in the union of these things. And we just computed that. So this should be m to the n minus the sum. Let me rewrite this a little bit just to be more organized. Plus m in k, m minus k to the nth power, 0k m. And notice that I can just absorb this minus sign here, turn this into a plus by removing this plus 1 up here, right? And there's a neat way of writing this, because what happens when k is 0? When k is 0, this term is just 1, since its product it doesn't matter. This term is just 0, right? M choose 0 is, of course, sorry, it's 1. It's 1. M choose 0 is 1. So we can also just ignore this one. And finally, m minus 0 to the nth power is just m to the nth power, right? So this term is actually inside this sum if we allow k to be 0. So if we want to be very succinct about this, which is not necessary, but we can just include the possibility of k being 0, and it turns out that everything works out fine. And this is the closed form formula to computing the number of surjective functions between two finite sets.